Hello, everyone. I'm William. I'm one of the co-founders at NanyML. Prior to NanyML, I was just a regular data scientist. I still am, by the way. But with NanyML, we tried to focus on post-deployment data science, which is all of the data science that happens after a model finds its way into production, which means performance, making sure that the models don't deteriorate, doing maintenance, optimization, and today we organized a webinar specifically about actionable performance monitoring in the context of demand forecasting models. And actionable means that you monitor performance and that then you know what to do after. And I'm going to just delve straight in because I see that's already 2 minutes past. So people can just come in and feel free to drop any questions in the comment section or in the Q&A. A quick overview of what we're going to discuss today. This webinar is organized by opinions from different people. And these are all very strong opinions, but weakly held. So if you have seen something else, or if you've experienced something else in practice or with your specific use case, that be sure to first share, first of all. And then, of course, it doesn't apply to everything. So that's why they're weakly held, but strongly communicated. And we're going to look at a few opinions from experts from other industries, also what the lovely NanyML people think about actionable performance monitoring, what demand forecasting experts have told us that are using or open source library. And then I'm also going to share a little bit of research with regards to demand forecasting models and specifically how to monitor them in production. Maybe a few words first about what demand forecasting is. And it's basically, here you can see like the daily demand for bike sharing data set, where typically you would consider this historical demand, and then you would try to predict future demand. And demand forecasting is being done across a variety of industries like retail and e-commerce, where demand forecasting is crucial to manage inventory, avoid stockouts, and also in manufacturing. Demand forecasting is used to plan production cycles, but also hotels, airlines, travel companies, they use demand forecasting so that they can do better pricing, and also utility, energy companies, healthcare, telecommunications, and even agriculture, where demand forecasting would be a use case applied to yield production of crops. So it's really industry agnostic. And typically, if we look at the demand forecasting use case, there is some specific terminology to bear in mind. And I visualized some of the core concepts, one of which is the forecast horizon or the forecast window or the prediction horizon. And that's basically how far along in the future that we want to make our prediction. So imagine that we here have inference time. So when we make a prediction with a model, if we then want to predict for the next month or for the next few days or for the next few weeks, that is what's considered the forecast horizon. And the length of the forecast horizon depends on the specific needs of the business and the industry that it operates in. And for instance, in industries where production lead times are very long, like automobile or aircraft manufacturing, the horizon might be several months or a year. And in contrast with fast-moving consumer goods or online retail, forecast horizons might be very short, like days or weeks. And it's very important that this forecast horizon aligns with decision-making processes in business. That means if you want to take decisions with regards to your inventory on a weekly basis, then this forecast horizon should also be on a weekly basis. We also have the forecast lag or a gap, and that usually has to do with the freshness of the data or the recency of the data. If we have the inference time here when we make a prediction, usually it takes a little while before all of the data or the previous sales have come in. And that is basically the lag, or it might be that we make a prediction today that we're using data from last week. And typically the accuracy of the forecast decreases with the length of the horizon. So that means that the error goes up over time. This is, of course, due to uncertainty and variability over long periods. Customer demand is also not static. And therefore, it's common practice to regularly, as new data becomes available, to update your forecasts and also to potentially update your machine learning models. And when we look at the training window, that is basically the data that is being used to generate a forecast model. And it's the training window is how far we look back in time to our observations. It might be that we use training data that is a year old or 2 years or 3 years. And then we also have to specify like a window size. And this has also to do with how far we look back in time, but more on the level of when we create features. For instance, if we create lags, that means sales of yesterday or the week before, and how far we look specifically for those features back in time, that's the window size. And then the training window is basically how many data points of the past do we include in our training set. And usually demand forecasting can be at different levels. We can make forecasts product level or product category level or SKU level, or even at store level. And if we look at features typically that we include in a demand forecasting model, it might be time-based features to capture trends or seasonal effects, and holidays, events, and features that capture promotion or discount events, product description or information, and of course, what's very important, the past sales or the lagged features. And these tend to have lots of impact, and there's also lots of information contained into the sales from last week or the demand from months before. So now that we've set the basis for what is considered demand forecasting, we're going to first look at some opinions of experts from other industries that are not necessarily in e-commerce and retail manufacturing, and specifically to what for them actionable monitoring means. And one way of looking at an industry or how far they are along or how advanced they are is to look at regulation. And regulation is here, and it's coming for all of us with the EU AI Act that has put in place like a few days ago. But there's other industries that have already been regulated for a longer time, for instance, the financial industry. And we have lots of users in the financial industry, and the biggest thing that they tell us what is important to make monitoring actionable is to define ownership and who owns model monitoring. And in general, this is very simple, but there is 3 actors, which is the IT. This might also be your infrastructure team or your MLOps team, but MLOps might also be part of your data science team. But here it's just abstracted away as all the technical people that are not data scientists, just for separation of concerns. And then there's also the business, who might be the model owners, the ones that consume your predictions. And then you have the data science team, the people that develop the machine learning model. And typically, IT or the ML engineers, they're responsible for application and infrastructure monitoring. And when something goes wrong from that perspective, if your resources are not well provisioned or your compute is running out or you're running out of memory, then this is something that can be solved from that perspective. But when it comes to the performance of the machine learning model, it is really something you should own as a data scientist. And this is very important because you spend so much time understanding the data, understanding the problem, understanding the business, and you also have the most context that when something goes wrong, specifically from a data perspective, to understand and figure out why it went wrong and doing a root cause analysis. And that is also very important to then actually specify what the issue is, what the issue resolution strategies should be. And on top, monitoring is the gateway to doing post-deployment data science, and we should really look at models in production like that. And models are not deterministic. They make lots of assumptions, and these assumptions over time, they don't tend to hold, just like how it is with patterns changing. And even though in large, I'll give an example of a large technology company that we spoke with recently, where they set up their data science team as consulting to model owners that have specific requests for building use cases. And then the business was also, after the model was being developed, responsible for the model performance. And what happens then is that they don't really know how to interpret, and even when they do, they don't really have the means to go and figure out and fix things. So they will let the models deteriorate, and when then there is a real failure, at the end of the day, it will end up on your plate anyway, because you'll, as a data scientist, get accused of building a bad machine learning model. So to make actionable monitoring, it's very, very important that you bring model monitoring to yourself that you care about your models that make it into production, then there's lots of things to learn after model makes it into production, and specifically monitoring the performance. And then when there is an issue, that you can go and figure out what went wrong. So that's this first little nugget from other industry experts that are not necessarily doing demand forecasting. We're also going to have a quick look at what the people at NanyML think about actionable monitoring. And we've actually created a monitoring workflow that we try to spread in the world. Let me frame it like that. And it's a monitoring workflow really specifically focused on performance monitoring. And the reason why we want the monitoring systems to be focused on performance monitoring is that because there's basically two paradigms. It's either performance or data drift. And in some cases, you can't measure performance because you're waiting for the ground truth or it's not available. And then you might decide that the monitoring system starts being centered around data drift, and that the data drift signals are the ones that you focus on. But there's lots of issues with data drift, and specifically for demand forecasting. And I'll come back to that a little bit later. But the key thing here is to monitor performance, and if you can't monitor, to estimate it. And we've developed a few algorithms that can do that. But what allows you to do that is that you only have to track one metric, which is your performance metric. And it's only when this metric goes down that then you actually flag performance degradation, and that you go and figure out what went wrong. And when you go and figure out what went wrong, it's then when you can use the typical data drift detection algorithms that you then can correlate certain alerts with performance. And then you can also leverage your domain expertise and the business understanding that you have as a data scientist while you build this use case to figure out what went wrong in production. And then after you've identified what went wrong, and part of this can be automated, but also not fully, very important, you can come up with the proper remediation strategy. And that might be to retrain the model. It might be also to adjust some of the downstream processes, which, for instance, with demand forecasting might be inventory management, or you might bring a human in the loop, which might be part of the downstream process to check certain forecasts manually. You might revert back to a previous model that you know is working, refactoring the use case, where you would really go back and see which features are needed and really build. But you can also decide to do nothing and let things deteriorate. And that's also very important, because as soon as you have observability and you have a view on performance, you can also kind of measure what the impact is of trying to remediate. And sometimes as a data science team, you have so much on your plate that trying to fix old models that have deteriorated slightly is not the best thing to do in terms of what value you can bring as a team. And you can just decide to also let it consciously deteriorate. But it's about deliberately taking that decision. So how does this monitoring workflow look in practice? So we start obsessing over performance, and that means that we will estimate the model performance if we can't, when we don't have ground truth, specifically for demand forecasting. If we have a very long forecast horizon, it's going to take a while before the actual demand becomes available, which we need to measure performance. And for that reason, we use a performance estimation algorithm. We have one in the open source library. And what this performance estimation algorithm does, it basically leverages the test set, and it goes and it basically maps which observations are tied to, or which types of observations are tied to which types of certain or uncertain regions in the model performance space. And then when the production data comes in, it can kind of map if there's more observations popping up in an uncertain region, then the estimated error is going to go up, and we will speak of a degradation. And when that's the case, when there is a certain threshold exceeded, we'll have the data science team alert, and then we can look into perform a root cause analysis. Maybe some of the distribution of the model input features have changed, and tie in together what it actually is that caused the problem. And for demand forecasting, this performance estimation is specifically useful because, like I said, it takes a long time for the ground truth to become available, and it's only then that you can actually measure the real performance. So how does that look on a performance chart? If you would make predictions here, and this is your inference time, you would only really actually know what the realized performance is of your demand forecasting model of maybe a few months or a few weeks back. If you have estimated performance, you can actually already know at inference time how well your demand forecasting is going to do. And this is key because that allows you to act faster and actually act before there is a model performance issue. Because if there is a degradation alert, you can decide to then not execute the forecast, fall back on the previous model, maybe put something, so go and figure out, put things on hold, maybe take a heuristic approach, and not execute on things that you already know that are not going to perform well. And there's another reason why this performance estimation is so key in demand forecasting, and that's because covariance shift doesn't really work, or at least the traditional covariance shift detection. If you look at traditional covariance shift detection, where we look at how distributions change over time, it is already a very, very sensitive methodology because it's based on statistical methods where you only look at one feature at a time, and you apply many different statistical tests over time as well, and they're just bound to throw false alarms. And it's really all of these false alarms on a univariate level that make that if you don't use performance estimation, that you will get a lot of noise and lots of alert fatigue. And why is that specifically the case in demand forecasting? Because in demand forecasting, there's lots of trends and seasonality. And the traditional ways that covariance shift detection is set up with KS tests, they don't deal very well with seasonability and trends. And a seasonality effect or a trend effect might something be that your model just is allowed to deal with very well because it has observed those patterns in the past. And then you don't want to get an alert if you see that every other month the distribution looks like this, or that this distribution looks like that, while you're using here the gray distribution as a reference. Whereas technically, if you would be using just statistical tests, this would all be an alert while it is expected behavior, and your model knows how to deal with it well. And that's a little bit the way to look at covariance shift, is like if there's unimportant features that drift, your model might be able to deal with that very well. Then there's another point which makes covariance shift detection not very relevant for demand forecasting. And that's with demand forecasting, we usually aggregate lots of data. And when we aggregate lots of data, we lose data points and information. And that means that typically we just make predictions for a few products or for a few categories, and then it doesn't really have statistical relevance if you look at a few products, or if you look at a product level and the inputs related to that product that goes into the model. If you want to compare it with last time, you might not be able to actually construct a distribution. So for that reason, it's way, way, way more efficient to use a performance estimation algorithm where you focus on one metric that you communicate, that you track, and that you optimize for. And that's really the power that we see with performance estimation. And that's also kind of our opinion as the NanoML people on how to do monitoring demand forecasting models in production. Then we talked to a few demand forecasting experts over the past few weeks that are actually also using our library. And it's very curious to see how they actually leverage performance estimation in production. And some of them do something which is called post-deployment model selection. So when they're expecting a model failure, like what I just explained before, so you add inference time while the model input is made available, and you measure the estimated performance, and you know that it's already gonna not be that performant, you can revert back to a previous model, because there either might be some concept drift or there might be some covariance shift happening. Or you might also fall back to a heuristic, because if there is a data quality issue, your model input might actually be corrupted, and falling back to a previous model doesn't make any sense either, because the actual data that goes into it is not properly formatted or not reliable. We've also seen people using NanoML's performance estimation to choose an optimal model from a registry. And the way to look at it is actually as a smart way to ensemble different models and to pick a relevant model for a certain period in time. Imagine that you want to predict the demand for the next week, and you have a registry of 20 models. And the reason why you might have a registry of 20 models is because you're either working with very, very big data and it's super expensive to retrain and refit machine learning models, or you might take the conscious decision to build different machine learning models for different regions. Or you might actually also taken the decision to specifically overfit your machine learning models, or specifically create machine learning models for, in the case of rare events. And then you can just all try them out at inference time and pick the model or pick the forecast that has the highest expected performance or the lowest error, and execute on that forecast. And that's something that we've seen people using 9ML's performance estimation for as well. And of course, when we're launching a new product or we're opening a new store, there's not that much data also about past sales. And then there is other ways to also leverage performance estimation, where we maybe go and look to similar stores or similar products and try to make an educated guess. There is also the rabbit hole that many experts talk about, which is automated retraining. And the narrative that has been pushed over the past few years is that more data, and maybe also more recent data, is always better, which is not necessarily the case. And specifically for demand forecasting, there is this thing where you increase your training window, that you have more data. It might increase your performance, but it might also have a negative impact on your performance, because if patterns are changing very fast, we're including data that is no longer relevant for the problem that we're solving. And when it comes to MLOps maturity, there's also this narrative that's being pushed, like, yeah, the more advanced we are and the more we do automated retraining, the better it is. But the most catastrophic failures that we've actually observed over the past few years that we're doing machine learning monitoring is often the case when there's lots of automation and limited observability. And what does that mean? If you automate lots of things and you, for instance, retrain weekly, is that you also expose yourself to some of the risks that come along with automated retraining. Because, for instance, when there is a data quality issue, there's one thing to make bad predictions on bad data, but there is another thing to then also include that bad data in the retraining of your next model. And then these type of problems can propagate through the life cycle of the machine learning model. And when we retrain, the new model might not always be better. And specifically, if we have not validated our retraining schedule, or we've picked an arbitrary window, or we picked an arbitrary frequency of retraining, we might actually, the variance of the model performance might actually increase and also bring unnecessary computing costs with it. So this is really something that we've seen, that the whole automated retraining movement, it is something to be cautious about. And that's also been confirmed by other people, and specifically in the demand forecasting space. But of course, we wouldn't be 9ML if we would also kind of want to validate those assumptions with a little bit of research. So what we did is this is, by the way, ongoing research, and we'll write about it more in the next couple of weeks. But we basically pulled in the New York City yellow taxi data set, which is data from more than 12 years with regards to demand of taxis, yellow taxis in New York. And you can see here how this time series kind of is instantiated over time. Here we can see COVID, and we can see that the demand of the yellow taxi is going down over time. But then after COVID, it slightly resurfaces again. Of course, there is many reasons why demand is going down, because there has been Uber has been introduced. There's also been the green taxi that has been introduced that takes the long trip. And also this demand is strongly dependent on the availability of taxi drivers, because the yellow cabs are the cabs that you hail and not the ones that you call. But this is very, very rich data. And basically for every hour, we have all the trips that happen in that hour. We know what the fare is. We know how many people were transported. We know from which location to another location. So there's lots of opportunity to create very, very advanced features and to really build out a demand forecasting use case on this data set. There's been research published about the degradation of machine learning models over time. Something, it's a really great paper if you want to delve into it. But what the premise is, we already talked about it a lot, but what the premise is that they basically take a data set like this one, and that they're just gonna sample different training periods, different histories, and then make predictions on different future data points. And they sample a certain age. So it might be that you train your data on this month, but then you make predictions 6 months later. And when you make those predictions, your model is 6 months old. And that is the age of the machine learning model. And when people have run these experiments, it's a very elaborate experiment setup. It's like 32 data sets from 4 different types of industries. The financial industry, there is like healthcare data sets in there. And then they built various types of machine learning models. And then for every data set, they're sampling this age and this training period, and then they're comparing the error between when it's making predictions and at the moment it was being trained. And then you can kind of get this relative error over time as the model becomes older. And there's very interesting things that came to light with this paper. And it's basically that 91% of models, they could degrade over time. And the older the model is, this is the model age in days, the older the model is, also the higher the error, and the variance of the error also goes up, which is very interesting. So that means the older a model is, the harder it is to kind of predict how certain models, because they built models with gradient boosting, with random forest, with recurrent neural nets, and rich regression. And they all react to aging differently, which is very interesting. And we try to kind of repeat this experiment, but then for the yellow taxi demand forecasting. So what we did here is we did the exact same thing where we specified like a small buffer, because that is like being used for the training data. We sample a training period or a deployment date. We look back 1 year in time, and then we measure the age, and then we predict here on a test set, and then we compare the performance relatively to the performance during training. And we can see that here for this specific demand forecasting use case, we can see that actually the performance is pretty stable. But then as the age come up and as we go through almost half a year of data, really the machine learning model starts deteriorating pretty heavily. And of course, there is many different experiments that you can run with this data set, because of course you can kind of look back and increase the historical window size, which we also did. So we ran the same experiment where we would take 1 year's worth of data of looking back, 2 years worth of data, and 3 years worth of data. And what's very interesting for this specific experiment, and we're going to repeat this experiment for many different demand forecasting use cases, that we can kind of get an idea of how to optimally retrain and how aging manifests itself within this type of use cases. But you can actually see that if you do 2 years or 3 years worth of data, that you can actually lower the relative performance quite significantly, but that then the aging also happens faster. And this is very interesting, because that means that you can probably increase the performance, the absolute performance, but that you will have to decrease or make your retraining intervals faster. And this is also something that is in line with what the other people have recommended with demand forecasting use cases, is to, if you look at the historical training window, is to first do an expansion window where you add more data over time. And then when you find the optimal window, to then slide it and not, and basically take 2 years of data or 1.5 years worth of data and then sliding it, as opposed to keeping expanding it, because you found the optimal point where adding more data from the past will not contain extra information. On the contrary, it might actually hurt the performance. And we're also running an experiment right now what the impact of retraining is. And specifically, when we build a machine learning model, we fix the hyperparameter tuning. And then we retrain later with the same hyperparameters. And it will kind of bring in light what the age is and how hyperparameters themselves deteriorate over time. And we'll be writing this. It's going to be for next time because we didn't wrap up the entire experiment before this webinar. But there's also proper insights that are coming out from there. And be sure to follow us with that, because Santiago, he's doing an experiment. He's our data science writer and our developer relations person, and he's really looking into that deeply. But so stay tuned for that. And that actually brings us to the end of this webinar. We walked to 4 opinions from different relevant people that might have something to say. Again, strong opinions, weakly held. But if you want to make monitoring actionable, there's 4 things that you sure have to be doing, which is actionability requires ownership. If you want to make things actionable, you need to own model performance monitoring. And model performance monitoring is the gateway to post-deployment data science. And if you own it, it will help you to take action faster and also to take the right, correct remediation actions. Performance is king. Model performance is the most important thing. 90ML performance estimation can help you with that, to track one single metric, to communicate one metric, to optimize for it. And data drift detection in this context is a useful tool to do root cause analysis, but don't put it at the center of the monitoring system, because you will get overwhelmed with false alarms, and specifically in the context of demand forecasting, it might not even work. And then understand before acting, which means is figure out what went wrong first, do a proper root cause analysis. There is ways to automate parts of the root cause analysis, but not everything can be automated yet. We've developed the concept drift detection algorithm, which allows to diagnose better what goes better. But there's lots of monitoring solutions today that don't incorporate fully concept drift detection yet. And then a decision to retrain or a decision to act on what the plausible cause is might not be fully accurate. So there's lots of things that have to come in place, and still lots of things that have to be invented to properly diagnose automatically and remediate automatically what to do with a failure. And only when executed well, you can pick the right remediation. And yeah, not all issues can be automated yet. And then also beware of automation in the sense that observability comes first, and retrain only when necessary, and consider starting with the expanding windows and then switching to sliding windows later. And that's a wrap for this webinar. If you find it interesting, you can scan this QR code, and then you can get access to the recording of this webinar. And I hope you had a great time. And I think that's a wrap. Or am I missing something, Mafalda?
No, what a great webinar, William. Thank you so much for the presentation. No, that's a wrap for today. So thank you so much for joining us. And if you have any questions or you'd like to reach out to us, feel free to reach out on LinkedIn. There's also William's LinkedIn there. I'm sure he's more than happy to receive your messages. And yes, this is it. And I hope you have a great day.